Now that you've seen how to use an ice table and an equilibrium constant expression for a weak acid to determine its pKa, and now that you've hopefully looked up the table of pKa values in your textbook to see some of the values that are possible, let's flip things around. Let's look at the pH of some weak acid, in this case lactic acid, this guy over here, if we have a known pKa. You'll notice, by the way, that we're running into a lot of compounds with, or a lot of solutions with compounds in concentrations like this. There's a reason for that. When it comes to a lot of the equilibrium math that we're doing, it gets a little bit funky at very high concentrations. And you'll start to need to use a value called activity that you'll learn about if you take quantitative chemistry. For now, though, these are pretty reasonable kinds of concentrations and many kinds that you might run into in common problems in fields like biochemistry, for instance. So, with that said, where do we go from here? Well, anytime you're given any sort of problem like this, if you are not told the chemical reaction equation, you need to start by picking that out. So, this is a weak acid. One of the things we're going to observe is that even for a polyprotic acid, there's a separate equilibrium reaction for each of the protons leaving the acid. So, in the case of lactic acid, we're talking about an equilibrium that looks like that. Okay, what else do we need to have to get started? Well, we should probably have our Ka expression. And that Ka expression, not surprisingly, is going to look very similar to the Ka expression that we had for our acetic acid case. As we work through these kinds of weak acid problems, one of the things you'll likely notice is that you're seeing a lot of Ka expressions and a lot of chemical reactions that look really similar. I would still strongly recommend that as you work on solving these problems, you continue to write these out. They're a really good check to make sure you're thinking about the chemical reaction correctly. As we move forwards from these sorts of weak acid problems to look at other more potentially sophisticated examples, it's going to be important not to assume that you know what the chemical equation looks like in its balanced form unless you've actually seen it or determined it for yourself. So with that said, what other information do we need? Well, this expression is using Ka, but all we have is pKa. So one of the things that we'll want to do first here is convert our pKa into a Ka. To do that, we can use the same expression, or the same formula, that we used to convert from pH into H+ concentration. So in that case, 10 to the negative 3.86 means that our Ka for this particular case is going to be 1.4 times 10 to the negative 4. What does that tell us? Well, perhaps not a huge amount just yet. It does tell us one thing, however. We calculated our acetic acid, Ka, in our last segment, and when we did that, we found that it was a value around 1.8 times 10 to the negative 5. In this case, we got a Ka that's about 10 times bigger. That means that in this equilibrium, we would expect to relatively have more H plus forming. That means that we can already say we expect lactic acid to be a stronger acid than acetic acid. Now, let's move forwards in solving this guy. What do we want to do to figure this out? Well, I think it's time to set up an ice table. And let's put what we know into this table. Just as was the case last time, we know that at the start we had 0.05 molar lactic acid and no H plus or LAC minus present. Now here's where things get interesting. In our last case with acetic acid, we knew how much H plus must be forming because that was, well, the amount that we had measured from measuring the pH. In this case, we weren't told the pH. That's what we have to find. So we don't know what this value is. We just know that we're gaining some, for the moment, unknown amount of H plus. Now we can pull in the stoichiometry in that chemical reaction equation that you wrote to say that we must form the same amount of both our conjugate base and we must have consumed that amount of our lactic acid. So now, down at the equilibrium line, we know that the amounts we have at equilibrium will be that 0.05 minus x, x, and x. You might be asking yourself right now, I thought you said that this ice table was going to solve all our problems. Well, in a sense, it has. Let's combine what we've learned from this ice table with that Ka expression. In essence, let's plug everything in. We only have one unknown in this entire table, so we should be able to deal with that. We know our value of Ka, and we know at equilibrium what each of these concentrations should be, as long as we tolerate x showing up in the expression. So let's plug all that stuff in. Our expression is our Ka is equal to our concentrations of H plus, LAC minus, and our concentration of our conjugate acid remaining. That's a little heavy looking, but that's something that we can handle. And it can be handled in a couple of ways. In principle, this is a quadratic equation, and one that you could solve in any of the ways that you likely solved quadratic equations in high school. However, we can take advantage of the simplification that we made previously. You might recall when we were working with our acetic acid case, we said that we could really kind of neglect the amount of the conjugate acid that was being lost. Now, sometimes you can and sometimes you can't, but let's proceed through this problem to see what it would look like if we do that. So let's neglect that amount and solve. That means our new expression can be arranged to that. We could easily take the square root of this product to find our x. So if we do that, we find that x is equal to 2.6 times 10 to the negative 3 molar H+. Is that large enough that we should solve this using the quadratic equation? This is starting to get pretty close. That is, 2.6 times 10 to the negative 3 is a number big enough that it's talking about subtracting 1, 2, 3. That's starting to get close enough that you might want to consider solving this using the quadratic formula. In typical cases, this is going to be an accurate enough answer for most things you need to measure in the lab. Keep in mind, lactic acid is one of the stronger weak acids. So you can see that in most cases, it won't be necessary to do this. And for the moment, we're not going to right away. So, are we done? Well, not quite yet. Remember, we were asked to determine the pH of this solution. And we really haven't done that yet, have we? We found the H+ concentration that would go in here. But we need to, last but not least, convert this into pH. Remember, one of the most common ways I've discovered that people tend to make errors on problems like this is there are a lot of steps here. Right? We had to calculate Ka, we had to write out a chemical reaction equation and an equilibrium constant expression. We had to make an ice table and fill stuff into that ice table. There were steps involved. And over the course of those steps, it can be a little bit easy sometimes to forget precisely what the problem was asking. So it's a good idea to double check at the end of a problem whether you've really answered what the problem was asking at the start. So to do that, we'll want to plug in to our good old-fashioned pH equation, which gives us an answer of 2.59. You might recall that our acetic acid in the last segment, at the same concentration, had a pH of 3.02. So, as you might expect, a weak acid with a pKa value that is smaller is going to wind up giving you a more acidic solution. Up next, we're going to look at how to apply this same type of approach to a weak base.